Basics for data science. While this is common knowledge and most likely just a refresher for you, let's quickly discuss basic tenancy configuration concepts. Compartments. These are logical containers for organizing OCI resources. User groups, simply a group of users. Dynamic groups are special groups of resource principals. And policies, which are used to grant access to groups within compartments. Let's quickly discuss how these components work together to enable access to data science resources. Firstly, you assign users to appropriate user groups. Secondly, you create dynamic groups for data science resources. And finally, you create policies that grant access to data science resources within a compartment. Starting then with compartments. They allow you to organize and control access to your cloud resources. A compartment is a logical grouping of resources that can be accessed only by certain groups that have been given permission by an administrator. When configuring your tenancy, the first step is to make a plan of how you will organize your data science resources going forward. Once you've made a plan, you can start creating one or many compartments. We will demonstrate this at the end of the lesson. However, for now, let's look at the quick and easy three-step process to create a compartment. From the Identity console, go to Identity and select Compartments. Click Create a Compartment, enter a name and description, and then click Create Compartment. Now, moving on to user groups, which are individual users that are grouped in OCI and granted access to data science resources within compartments. Admins can perform three simple steps to create user groups. Firstly, create the users. Secondly, create the groups. And finally, add users to groups. When configuring groups, first decide how users will access resources in the compartments. Now, for a special type of group called dynamic groups that contain resources that match rules that you define. Resources such as data science notebook sessions, job runs, and model deployments can be included in a dynamic group. These matching rules allow group membership to change dynamically as resources that match those rules are created or deleted. These resources act as principal actors. They can make API calls to services according to policies that you write for the dynamic group. We'll discuss policies shortly. For example, using the resource principal of a data science notebook session, where its dynamic group has a policy which enables object storage access, you could make a call to the object storage API to read data from a bucket. So, resources match rules, and rules are applied to dynamic groups. Once you give your dynamic group a name and description, you'll fill in the following matching rules, where the compartment OCID is replaced by the identifier of the compartment you created for data science. In this example, with these rules, the dynamic group will be made up of any and all resources of these three types that exist in the compartment. What those resources have access to do, as mentioned before, will depend upon policies. Policies define what principals, like users and resources, have access to in OCI. Access is granted at the group and the compartment level, which means you can write a policy that gives a group a specific type of access within a specific compartment. Policies have a basic syntax. Allow a group called your group name to do some verb or action upon a resource type within a compartment named compartment name. Let's look a bit closer at each of these variables in the syntax. Group name, this will be filled in with the name of the user group or dynamic group. Verb, this will define the level of access. We will look at different verb types next. Resource type, this will specify the type of resource or resource family to be accessed. And compartment name, this will be filled in with the name of the compartment. Verbs define the level of access that would be permitted to the resource or resource family. Verbs include, from least to most permissive, inspect, which gives the ability to list resources without access to any user-specified metadata. Read includes inspect plus the ability to get user-specified metadata and the actual resource itself. Use includes read plus the ability to work with the resource, including updating it. Generally, this does not include creating or deleting permissions. And finally, manage includes all permissions, including creating and deleting. Resource type in the policy defines which specific resource you are writing the policy for. For example, data science includes resources such as data science models or data science jobs. You can write a policy for individual resource types. However, to make writing policies for related resources much easier, there are aggregate resource types, which contain a family of related resources. The aggregate resource type for data science is data science family. We are adding the color coding to make the syntax easier to understand here. But please note, these are actually the most critical of the required data science policies, not simply policy examples. The first required policy will be to allow data scientists to manage all data science resources in a specific compartment. To do this, your policy would say, allow your user group to manage data science family in your compartment name. The second required policy is to allow data science resources, such as a notebook session, in a dynamic group you've created to manage all data science resources. So this time, allow a dynamic group to manage data science family in your compartment name. The following policies are required to enable user access to metrics and logging for data science resources. First, allow your user group to read metrics in compartment name. Secondly, allow dynamic groups to use log content in your compartment. Thirdly, allow your user group to manage log groups in your compartment. And finally, allow your user group to use log content in your compartment. If you plan to use custom networking in data science, which is discussed in depth in the next lesson, you will need the following policies. Allow the service data science to use virtual network family in your compartment. Allow your user group to use virtual network family in compartment. And allow dynamic group to use virtual network family in compartment. The following policies are useful for accessing services related to data science, so you might find it useful to pause the lesson here and take note of them. To create a compartment from the Identity console, go to Compartments and click Create Compartment. Give your compartment a name and give it a description. In this example, I'm adding tags to keep my workspace clean and tidy. Click Create Compartment and wait a few moments for your compartment to be created. You may want to take note of the OCI ID of the compartment for later. To create a user, in the Identity console, navigate to Users and click Create User. Give your user a username and add a description. You can also add the email address of the user and then repeat this process for every user that you want to add. Click Create. Next, we'll create a group for our users. From the Identity console, go to Groups and click Create Group. Give your group a name and add a description. Then click Create. Once we have a user group created, we can begin to add users to the group. Click Add User to Group and then select your user and click Add. Repeat this process for all the users you want to add to this user group. Now moving on to dynamic groups. From the Identity console, go to Dynamic Groups and click Create Dynamic Group. Give your dynamic group a name and a description. Now we're going to enter some matching rules. And remember, we looked at the 3 important matching rules for data science resources. The first rule is for data science notebook sessions. The second rule is for data science model deployments. And the third rule is for data science job runs. And we're replacing the compartment ID with the compartment we created earlier in the demo. Click Create to create your dynamic group. Now, for the final step, we need to allow our resources and users to access data science in our compartment. So we're going to create a policy. Now in this policy, I'm going to cover the required data science policies. So I'm giving it a relevant name and description. In the policy builder, I'm going to switch to the manual editor to allow me to paste in my policy statements. Once I've added those statements, I'll click Create to create the policy. Now there were a few additional required policies specifically for users and dynamic groups to access metrics. So I'm going to edit this policy now and add additional statements that will allow access for my user group to read metrics in the compartment, for my dynamic group to access log content, for my user group to access log groups, and finally for my user group to access log content. And once I've added these statements, I'll save my changes. Now that we've covered the required policies, we did show some useful policies that it may be good to create as well, especially when you want resources or users within a data science service to be able to access other OCI services. So in this case, I'm adding some useful data science policies. Again, I'm giving a name and a description and switching to the manual editor to add my policies. These policies are specific for object storage, and so I want to allow both my dynamic group and my user group to manage the object family in my compartment. I can repeat this process for all the policies I want to add. So, to wrap up, we discussed tenancy configuration concepts like compartments, user groups, dynamic groups, and policies. We talked about matching rules for grouping resources into dynamic groups. We covered policy syntax for setting your policies. We discussed the required data science policies. We talked about policies for data science related services, and then covered some optional data science policies you might find useful. Thank you. Hello, I'm John Stainsby. In this lesson, we're going to show how to configure a tenancy with OCI Resource Manager. Instead of configuring your tenancy manually, you can use the Data Science Service template, which is pre-configured in Oracle Resource Manager. This template will automatically create the required user groups, dynamic groups, and policies for a basic use case. The Data Science Service template creates a user group with a name you define, a dynamic group with a name you define, and the following matching rules for resource types: data science notebook session, data science model deployment, and data science job run. It also creates a policy with a name you define and the following statements to allow your user group to manage data science family in your compartment, to allow the dynamic group to manage data science family of resources in your compartment, to allow your user group to read metrics in your compartment, and to allow the dynamic group to use log content in your compartment. We will demo this at the end of the lesson. Let's run through the general process of running the Oracle Resource Manager, or ORM stack for short. Firstly, create the stack, then select your template. Next, select your compartment and run the stack. Finally, add users to your user groups. Remember, templates are only available on the console, and you can always edit your stack later. As we've discussed, you can configure your tenancy with the Resource Manager using a predefined data science sample solution, but that's not the only option. You can also use your Terraform script located at this public GitHub repo. Now I'm going to show configuring a tenancy with OCI Resource Manager. Navigate to Resource Manager and then click Stacks. Click Create Stack, select Template as your origin, and select Template. From here, I'll go to Service and choose Data Science. Then click Select Template. From here, I can scroll down and choose the compartment that I want to use for my data science resources, and click Next. There are some additional variables I can complete if I choose. Click Next to move through the wizard. And then finally, I want to run Apply on my stack immediately. Click Create. And wait for this job to run. After running the stack, all you need to do is add your users to the user group that this configuration creates. You can also access the Terraform script at this public Git repo. To wrap up, we discussed automatic configuration and the data science service template. We talked about the resources that the template creates, like user groups, dynamic groups, and policies. We covered the steps to run the ORM stack and where to access the Terraform script on the public GitHub repo. Thank you. Hello, I'm John Stainsby. In this lesson, we'll look at networking for data science. Let's begin by introducing a few useful cloud networking components. We'll define these components and give a very high-level introduction to these concepts so that you can understand how they relate to data science. But please note, this course will not go in depth on networking topics. The first component to know are virtual cloud networks, or VCNs. The next are subnets, as well as virtual network interface cards, or VNICs. Also, dynamic routing gateway, or DRG, network address translation gateway, or NAT, and finally, service gateway. Let's show how all these networking components work together. The VCN is a virtual private network that you set up in Oracle data centers. The subnets are subdivisions you define in a VCN. These subnets contain VNICs, which attach to instances. Subnets act as a unit of configuration within the VCN, so all VNICs in a given subnet will use the same route table, security lists, and DHCP options. These VNICs determine how an instance connects with endpoints inside and outside the VPN. Then there are three types of optional virtual routers you can add to your VCN. A DRG provides a path for private network traffic between your VCN and on-premises network. You can use it with other networking components and a router in your on-premises network to establish a connection by way of site-to-site VPN or Oracle Cloud Infrastructure Fast Connect. It can also provide a path for private network traffic between your VCN and another VCN in a different region. A NAT gives cloud resources without public IP addresses access to the internet without exposing those resources to incoming internet connections. Finally, a service gateway provides a path for private network traffic between your VCN and supported services in the Oracle Services Network. For example, database systems in a private subnet in your VCN can back up data to object storage without needing public IP addresses or access to the internet. In the data science service, you can create a few different types of resources that can execute custom code for different use cases. These resources include notebook sessions, jobs and job runs, and model deployments. In this lesson, we will refer to these types of data science resources as workloads. Oftentimes, you will want to access external assets from your running workload, such as code files, data, libraries, secrets, and logs. You may also want to create and run other workloads on data science, or workloads on another platform like Dataflow. These external assets could be accessible over the public internet, or they could be in a private network. In order to access these external assets, you must ensure network connectivity between your workload and the network location of your desired assets. In data science, there are two networking patterns that you can use: default and custom. When you select default networking, the workload will be attached via a secondary VNIC to a pre-configured service-managed VCN subnet. This provided subnet will allow egress to the public internet through a NAT gateway and access to Oracle Cloud Services through a service gateway. Therefore, if you only require access to the public internet and/or OCI services, this is the fastest, easiest way to get started on the service, as it does not require you to create your own networking resources or write policies for networking permissions. When you select custom networking when creating a data science resource, you'll specify a pre-existing subnet that's owned by your own tenancy that you want to use for data science workloads. When the workload is created, the data science service will connect to your selected subnet through a secondary VNIC attachment. This bring your own network configuration, achieved through custom networking, will allow you to have access to resources and assets as defined by your subnet. If you require access to external assets that reside in a private network, such as code files in an enterprise Git repository server, or data in an on-prem database, you'll need to use custom networking to ensure connectivity for your workloads. Please work with your tenancy networking administrator to configure your VCN subnet for data science. As discussed in the lesson on tenancy configuration, you will need additional policies to use custom networking in data science. I'm going to show you a quick way to get set up with networking for data science. To do this, we're going to use the VCN wizard, so navigate to Networking and Virtual Cloud Networks. Click on Start VCN Wizard, and then choose Create VCN with Internet Connectivity. When we start the VCN wizard, we just need to give our VCN a name. As we scroll down, there are a number of options more likely to be used for advanced users. If you want to continue with default networking, simply click Next and click Create. Wait a moment while various resources are created for you in your compartment. Once it's done, click View Virtual Cloud Network. We can now see that our network's been created. If I go back to the Virtual Cloud Network screen, you can see my example DSVCN is now created. Please note that you won't need to complete this step if you configured your tenancy using OCI Resource Manager as per this example, the VCN is created for you. In this lesson, we looked at cloud networking components and definitions, an overview of how those components fit together, and the two network connectivity options, default networking or custom networking. Thank you. Hello, I'm John Stainsby. In this lesson, we'll look at how to authenticate to OCI APIs. Data science resources, such as notebook sessions, jobs, and model deployments, allow you to execute custom code. As a part of your code, you may want to interact with other OCI services via the OCI REST APIs. For example, this would enable you to read and write data to object storage from a job, or create and run data flow applications from a notebook session. In order to interact with the OCI APIs, you'll need to operate as an authenticated user. Most commonly in data science, you'll interact with the OCI APIs via the ADS SDK, the OCI Python SDK, or the OCI Command Line Interface, or CLI. This lesson will explain the options for handling authentication for each of these interfaces. Please note, this lesson is only concerned with authentication, which is to say, the process of verifying a valid OCI recognized identity or principal. It is not concerned with authorization, which refers to the access level that a principal has permission for. We will assume authorization has been covered in Lesson 2 of this module, Tenancy Configuration. A resource principal is a feature of Identity and Access Management, or IAM, that enables resources to be authorized principal actors that can perform actions on service resources. Each resource has its own identity, and it authenticates by using the certificates that are added to it. These certificates are automatically created, assigned to resources, and rotated, avoiding the need for you to store credentials in your notebook session or job. The data science service enables you to authenticate by using your notebook sessions or your job runs resource principal to access other OCI resources. Resource principals provide a more secure way to authenticate to resources compared to using the OCI configuration and API key approach. They provide a more practical way to authenticate from a job run, which doesn't provide you with an interactive interface like notebook sessions for creating and moving around config files. If you don't explicitly use the resource principals when invoking an SDK or CLI, then the configuration file and API key approach is used. The resource principal token is cached for 15 minutes. If you change the policy or the dynamic group, you'll have to wait for 15 minutes to see the effect of your changes while the cache expires. The code used to set resource principals as the authentication mechanism varies slightly depending on the interface you are using. You may want to pause the lesson here and take a note of these. You can operate as your own personal IAM user by setting up an OCI configuration file and API key to access OCI resources. This is the default authentication approach when using ADS, the OCI Python SDK, or OCI CLI. To authenticate using the alternative configuration file and API key approach, you must upload an OCI configuration file into the notebook sessions OCI directory. For the relevant profile defined in the OCI configuration file, you'll also need to upload or create the required .pem files. Instead of uploading existing OCI configuration and API key files, you can use the API_keys notebook to create them. To launch the API_keys notebook, click Notebook Examples on the Jupyter Lab Launcher tab. We discussed the importance of authentication in data science, the need to authenticate different interfaces, the definition of resource principals, how resource principals and the data science service work together, and how to work with resource principals in different interfaces. We also looked at OCI configuration files. Thank you. Hello, I'm John Stainsby, and in this first lesson we're going to cover the principal component of a data science workspace, a project. Let's start out with a definition of a data science project. It's a collaborative workspace for teams of data scientists to organize their work around a particular use case or business question. All data science resources, for example, notebook sessions and models, are created within projects. Data scientists can create, name, describe, and tag their projects. There are two main ways to create projects, from the console user interface and from the ADS SDK. We will demonstrate both ways to create projects at the end of this lesson, but for now let's look at each option at a high level. From the console, log into your tenancy with the necessary policies. Open the navigation menu, click Analytics and AI. Under Machine Learning, click Data Science. Then click Create Project and select the compartment you want to add the project to. It is optional but recommended to enter a unique name for the project. If you don't provide a name, then a name including the current timestamp is automatically generated for you. Also optionally, enter a short description for the project. If you don't add a description, it remains empty, but descriptions are useful for other users to understand what your project is, independent from any specific naming convention that you might choose to use. Add tags to easily locate and track the resource by selecting a tag namespace, then entering the key and value. To add more than one tag, click Add Additional Tags. To view the details for your project immediately after creation, select View Detail page on clicking Create. After you successfully create a project, you can create notebook sessions and models and associate them with the project. You and your collaborators can then organize and document your data science work within the projects. From the ADS SDK, using the project catalog object, create a project by calling the createProject method and specifying the compartment ID. In this code example, we use a preset environment variable of a notebook session to use the same compartment as the notebook session itself. Let's talk about managing projects. In particular, let's discuss viewing, editing, and deleting them. You can view all projects on the project list page. Click a project to view its details. Projects have the following metadata: a display name and description, the OCI ID of the project, the date and time it was created and the user it was created by, as well as its tags. The only fields that are editable are display name, description, and tags. You can view and edit projects through any of the OCI interfaces. To delete a project must be empty. All data science resources associated with that project must first be deleted. To delete a project from the console UI, locate the project in the project list, then, from either the project list or the details page, click Delete. In order to delete a project from the console, you must fill in the display name of the project to confirm deletion. To create a project, first navigate to Data Science. You'll land on the Projects Lists view. From here, click Create Project and give your project a name. Also give it a description. And I like to use tags to keep my workspace tidy. Then click Create. You'll immediately enter the project view. From here, click back to the Projects List view to see your project listed. To edit a project, either from the project page or from the menu, select Edit, and the only fields that are editable are the name and the description. In order to edit tags, you would click on these dots, view the details, select the tags, and choose from your freeform tags and edit or add your tags from there. To delete a project, either from the list view or from the project view, simply click Delete. Bear in mind that a project must be empty in order to delete it. Type in the name of the project exactly to confirm deletion and click Delete, and you'll see the project move to a deleting status. It's now deleted, and when you go back to the project view, you'll be able to see the deleted status. You can filter out any projects that are deleted by choosing a different state. So if we go to active, we won't see any projects anymore. So in this lesson, we discussed data science projects, how to create them, and how to manage them, including viewing, editing, and deleting. Thank you. Hello, I'm John Stainsby. In this lesson, we're going to cover notebook sessions. Let's start out with a definition of data science notebook sessions. They are the Jupyter Lab interface for building and training your models. Notebook sessions are fully managed by the service, which means that all underlying infrastructure is managed by the service also. In short, you don't need to worry about interacting with the compute or storage APIs for provisioning or lifecycle management. In addition, all software updates and patching is handled by the service. They offer support for both CPU and GPU shapes, and they provide persistent session storage for data, notebooks, and environments. We will demo this at the end of the lesson. However, let's run through the general process of creating a notebook session from the console. Once you have a project created, to create a notebook session from the console, navigate to your project details page and click Create Notebook Session. Select your desired compartment from the drop-down list. Optionally, give your notebook session a name. Select your compute shape. You can choose from a variety of shape families that provide different hardware, including AMD CPUs, Intel CPUs, and NVIDIA GPUs. Input a value for the size in gigabytes of block storage that will be attached to this notebook session. The minimum value is 50 gigabytes and the maximum value is 10,240 gigabytes. Select your networking type, depending on what you need to access from this notebook session. If you select Custom Networking, select your desired VCN and subnet. Then click Create. Remember that notebook sessions do take a few minutes to start up. When your notebook session is active, you will see the Open button enabled. Let's talk about managing notebook sessions. In particular, let's discuss viewing, editing, and deleting them. You can view all notebook sessions in a project on the Notebook Sessions list page. Click a notebook session to view its details. Notebook sessions have the following metadata: a display name, an OCI ID, the date and time it was created and the user it was created by, its compute shape and the amount of storage in gigabytes, VCN and subnet, and its tags. When a notebook session is active, the only field that's editable is display name. You can view and edit notebook sessions through any of the OCI interfaces. Note that any files or changes on the notebook sessions file system that have not been backed up or committed will be lost when you delete the notebook session, as the compute instance will be terminated and the block volume will be destroyed. To delete a notebook session from the console UI, locate the notebook session on the project details page from either the notebook session list or details page, then click Delete. In order to delete a notebook session from the console, you must fill in the display name of the notebook session to confirm deletion. To activate a notebook session in the console, click Activate on the details page or from the notebook session list page. When you click Activate, you'll be prompted to select the compute, storage, and network configuration. At this stage, you can either keep the same settings or update the configuration. You can use this capability to scale your notebook sessions up and down over its lifecycle, depending on how your compute power requirements evolve as you do your model building. When you confirm to activate, your notebook session will change to an updating status. When the infrastructure provisioning completes, it will switch to an active status and you'll be able to open the notebook session. This can take a few minutes. To deactivate a notebook session in the console, click Deactivate on the details page or from the notebook sessions list page. The notebook session will change to an updating status while the infrastructure deprovisioning completes. When complete, the notebook session will be in an inactive state. You can deactivate a notebook session to save on compute costs. When you deactivate a notebook session, the compute instance is shut down, while the block volume attached to it is retained. So you can save your code, data, and files to the block volume to save your progress. To be clear, any data on the boot volume of the notebook session is deleted after you deactivate it. When you reactivate the notebook session, a new compute instance is started up and the existing block volume is attached to it, enabling you to pick up from where you left off. You can also view metrics for a notebook session over the course of its lifecycle on its details page. Metrics include CPU and memory utilization, expressed as a % of total, and network traffic in and out, expressed as a number of bytes. To create a notebook session from the console, once you have a project created, navigate to the project details page. This is the project I created in the previous lesson, and click Create Notebook Session. Give your notebook a name and select a compute shape. In this example, I'm going to take a standard 2.2 and configure your block storage size. I'm just going to go for the minimum of 50. I'm going to choose my default networking, but if you were choosing custom networking, you would click here and select your VCN from this list. And I'm going to add a tag And I'm selecting to view the detail page when I click Create. Now I click Create, and it will take a few moments for the project to be created. However, when the notebook session is active, you'll see an Open button up here enabled. You can see that the notebook session has the following information. Its OCI, who it was created by and when it was created, the compute instance shape and block storage size, the VCN and the subnet, and how many OCPUs and the amount of memory on the instance shape. This notebook's now active, which means the only field that is editable is its display name. To deactivate a notebook session in the console here, we're going to click on the Deactivate button from the details page. The notebook session will change to an updating status while the infrastructure is deprovisioning, and when it's complete, the notebook session will be in an inactive state. When you reactivate the notebook session, a new compute instance is started up, and the existing block volume is attached to it, enabling you to pick up from where you left off. To activate a previously deactivated notebook session, from the notebook session details page, click Activate. We'll be prompted to select our compute shape once again. We can leave it the same as before, or we can select a new one. As I mentioned, you can use this capability to scale your notebook session up and down over the course of its life cycle. Once we click Activate, the session will change to an updating status and the infrastructure provisioning begins. When it completes, it'll switch to an active status and you'll be able to open the notebook session. It can take a few minutes. To delete a notebook session from the console UI, from its detail page, click on More Actions and then Delete. I'll need to enter the name of the notebook session in order to delete it, and note that any files or changes on the notebook session's file system that haven't been backed up or committed are lost. This is because the compute instance is destroyed as well as the block storage. Click Delete to confirm, and the notebook will move to a deleting status. Once it's deleted, it will move to a deleted status. To wrap up, we defined notebook sessions and we talked through the steps to create a notebook session from the console. We discussed how to manage notebook sessions, such as how to view, edit, and delete them. We explored the notebook session metrics and how to activate and delete notebook sessions. Thank you. Hello, I'm John Stainsby. In this lesson, we're going to cover how to work with Jupyter Lab. Jupyter Lab is a next-generation web-based user interface. It's also the interface for notebook sessions. The reason we use Jupyter Lab interface and notebook sessions is because they're familiar to data scientists who can easily navigate the interface, which makes for easy adoption of the data science service. It enables users to work with and integrate documents and activities, including Jupyter notebooks, text editors, terminals, and custom components. It allows for interactive computing and understands many file formats such as images, CSVs, JSON, Markdown, PDF, as well as Vega and Vega Lite. Let's quickly differentiate between Jupyter Lab as an open source tool and what you'll see in the data science console. While the menu structure and layout is identical, there are three main differences in the data science interface. As we'll see next, the launcher provides easy access to your notebooks, console, text editor, terminal, environment explorer, and notebook examples. The Environment Explorer, which we'll talk about in the next lesson, is a GUI tool that allows you to manage and search for Conda environments. Finally, the GitHub extension, which we'll discuss in Lesson 9, allows customers to easily use Git to version control their code inside the notebook session. There are several features of Jupyter Lab that we will discuss in the coming demo. Perhaps three of the most prominent are the menu bar at the top of Jupyter Lab, which has top-level menus that expose actions available in JupyterLab with their keyboard shortcuts. The launcher, as mentioned, provides easy access to the most common items. As with menus, keyboard shortcuts, and the command palette, new items can be added to the application launcher via commands. The left sidebar contains a number of commonly used tabs, including File Browser, List of Tabs, Command Palette, Table of Contents, and Extension Manager. Some other features and functionality that we'll explore in the demo include the main work area in JupyterLab, which enables you to arrange documents and other activities into panels of tabs that can be resized or subdivided. The work area has a single current activity. The tab for the current activity is marked with a colored border, which is blue by default. Code consoles provide transient scratch pads for running code interactively with full support for rich output. Kernel-backed documents enable code in any text file to be run interactively in any Jupyter kernel. Multiple views of documents with different editors or viewers enable live editing of documents reflected in other viewers. With kernel management, accessible from the kernel menu, users can access actions for managing kernels, which are separate processes for running code. Then, the right sidebar contains the property inspector, which is active in notebooks. All user actions in JupyterLab are processed through a centralized command system. These commands are shared and used throughout JupyterLab. The command palette provides a keyboard-driven way to search for and run JupyterLab commands. Let's start with the top Chrome bar. On the left, you'll see the Oracle logo. Clicking this will bring you back to the Cloud Console homepage. Next, to the right, you'll see your notebook session's name. If you click on this, you'll navigate back to the notebook session details page within the Oracle Cloud Console. Next, over to the right, you'll see Session Remaining. You're automatically logged out of a notebook session after an hour of inactivity by default. You can change this behavior in each notebook and extend the notebook session time by up to 23 hours for a total of 24 hours. Next, the help icon will take you to some useful OCI documentation, and lastly, you can sign out of the notebook. Next, let's look at the left sidebar. The top icon is for the file folder browser. You can navigate into and out of directories. And you can open files by double-clicking them. You can also add folders and delete folders. The next item down is the terminal and kernel sessions running within the notebook. You can stop a process from running from this view by clicking Shutdown. The next item down is an extension that assists with working with Git. This is covered in a different lesson, so we're not going to go into depth here. The next item down is Commands, and this gives you access to all the commands in JupyterLab. You can use the search to find a specific command, such as the variable inspector. The next item down is the property inspector. And the next item will show you all of your open tabs in a list. The next item is your table of contents. This tool will pass the markdown of notebook files and show you the table of contents that allows you to navigate through different sections of the notebook file. The last item will show you any additional extensions you have installed in JupyterLab. To hide the left sidebar, simply click any of the icons twice. You can open the launcher anytime by clicking the plus icon from the Folder Browse toolbar, or by going to the File menu and selecting New Launcher. You can close tabs like this. The launcher provides easy access to your notebooks, console, text editor, terminals, environment explorer, and notebook examples. We'll walk through the launcher now. At the top of the launcher, you get quick access to documentation about the Environment Explorer, notebook examples, and how to get started for the first time. As we scroll down on the left side, you'll see two useful extensions, the Environment Explorer and Notebook Examples. The Environment Explorer extension helps you discover Conda environments that you can install and track the Conda environments that you already have installed in this notebook session. The Notebook Examples extension will help you discover and access tutorials and documentation for how to work with different features of the service and complete different use cases. The right side of the launcher allows you to easily create new files and sessions. When you click an item in the kernel list, you can create a new notebook file or a console session using that kernel. We'll come back to this in a moment. The other list will create terminal sessions or other types of file like Markdown or text files. So let's create a new notebook using the Python 3 kernel. Click on the Python 3 kernel and select Create Notebook. When you create a new notebook, the service populates some useful tips at the top of the file. These tips help you check for internet connectivity, access help documentation, gives you some typical imports and settings for ADS, and also some useful environment variables. When you've created a new notebook, you can rename it by right-clicking on it and clicking Rename, and typing new name. You can run code in the cells by writing your Python code in the cell and then running the cell. For example, we can ask it to print Hello World. You can run code in cells a number of ways. You can click the triangle icon to run the selected cell. You can use the Run menu and choose Selected Cell, or you can use the keyboard shortcut Shift-Enter. While the code is running or is queued to run, there will be a star icon to the left of the cell. When it's complete, it will show a number that counts the order that the cells were run in a notebook. You can change the type of cell by choosing the drop-down menu that says Code and selecting a different option, for example, Markdown. You can document your code cells by writing Markdown in other cells. For example, we'll write #title to create a title. You can change the order of cells by clicking on the left side and dragging the cell up or down. Let's explore some of the options in the Edit menu. For example, we can click in a cell and go to Edit, and then we can merge selected cells. We can also split the selected cells. You can change the kernel of the notebook by clicking the kernel name in the top right and selecting a different kernel option. Now let's look at a more complicated notebook by looking at a notebook example. So we'll go back to the launcher, select our notebook examples, and in this pre-installed Conda environment, which I added but you will learn how to do in detail in a later lesson, the following notebooks are available, and I'm going to choose the binary classification attrition and click Load Example. Now that it's loaded, I can go and run all cells. While this is running, if I want to stop the process, I can go to the kernel menu and select Interrupt Kernel. This is the same as using the shutting down kernel tool as shown before. Since this notebook ran part way, I can show the variables that were set by going to the Variable Inspector. Let's say I want to see the variables side by side with my notebook, or have two tabs visible. If I click on the tab and drag it around until different parts of the screen are highlighted blue, and release it, I can now see my notebook and my Variable Inspector side by side. To go back to full screen, I'll drag the tab back to the blue box on the title bar. Let's explore some of the options in the View menu. Back in my attrition notebook, for example, if I want to show line numbers, I can select View and Show Line Numbers. You can use the View menu options to collapse cells, such as Collapse All Code. You can also collapse all outputs. You can expand cells using the expand options, like expand all outputs. Let's explore some of the Jupyter Lab settings. For example, you can change the theme. Let's go back to the File Explorer. You can create new files by right-clicking here, or you can also upload files by dragging and dropping them into the file browser. Let's try that with a CSV. Depending on the file type will depend how Jupyter Lab allows you to view the file, but a CSV is going to show you the columns and rows of your data. Let's go back to the launcher and open up a terminal session. You can use standard Linux commands here, for example ls, to see a list of files. Other command line tools such as odsc conda CLI, the git CLI, and the OCI CLI are installed here. Lastly, within Jupyter Labs, there's a help menu that gives you access to reference material, FAQs, and help documentation. So, in this section, we discussed an overview of Jupyter Lab, how the different interfaces compare. We talked about many features and functions of Jupyter Lab, and showed how to navigate Jupyter Lab. Thank you.
Hello, my name is John Peach and I'm a data scientist on the Oracle Cloud Infrastructure Data Science Service. In this module, you'll learn what a conda is, why you should use them, and how they are managed within the data science service. What is a conda environment? Well, for starters, a conda is an open source package management environment system. It allows us to bundle up software such as the interpreter, Python modules, external libraries, and other programs into a single environment that we can use. So what are some of the benefits of using a conda? Well, first, it allows us to install the packages and only the packages that we need, or use an existing conda and just update the packages that we need to update. Second, it allows us to isolate different software configurations. For example, you may have one configuration for doing computer vision models, and that uses a different set of libraries than, let's say, a model that you're building using linear regression. So we can isolate these configurations so that they don't collide with each other. It allows us to then switch between these environments. So I can have one for computer vision where I have all my computer vision tools, and then I can switch over to one that allows me to do linear regressions without bringing all the powerful tools that I need for computer vision and their large libraries. In addition, it allows me to share these configurations with others. So once somebody on your team has set up a configuration to do some particular type of modeling, that can be shared across the team, and not everyone has to reproduce that work. One of the more powerful things within the data science environment is it allows you to have a configuration in a conda pack that you use for your notebook. But then when you want to deploy a model that you built or run a job, you can bring that conda pack along with it, so you don't need to configure it again. And you know that the job and the model deployment are going to run in the same environment in which the model was trained. Another very important advantage of a conda is that it allows you to leverage reproducible research. As packages change over time, the computations may change and the results may change. If you want to go back and figure out why a model isn't working particularly well, you can go back to the exact versions of the software that you use to build the model. To work with conda environments, the Data Science Service has developed the Environment Explorer. The Environment Explorer is a graphical user interface that you can see here on the right that allows you to explore and manage conda environments. And within the service, there is 3 types of conda environments. There's the data science conda environment, a published conda environment, and those conda environments that you've installed. Environment Explorer allows you to discover information about particular condas. It has different views where you can see it as a card view or a list view. If you're looking at many conda environments, the list view is very helpful. If you want to know details on a particular conda environment, the card view is very helpful. It also provides a search mechanism. So you can type in keywords and search for the conda environments that you want. You can also apply filters. So let's say you're running on a GPU. You can say, just give me the conda environments that run on GPUs, or you can filter out conda environments that have been deprecated by the service. So the first type of conda environment that I want to talk about is the data science conda environments. These conda environments are managed and curated by the data science service team. They're built to serve customers' needs. So some of them are focused on particular piece of software, like there's ones for PyTorch and TensorFlow. Other ones are for particular industry verticals. So we have a conda environment for healthcare, for example. And we also have conda environments that are built around general purpose tasks, such as doing exploratory data analysis. Each one of these conda environments provides specific tools and frameworks for doing your data science tasks. They provide a comprehensive environment to solve your business use cases. So they're designed to have the right software in there for most customers. And you can look at just the data science conda environments by filtering for them in the Data Science Conda Environment Explorer. Next, we have published conda environments. So published conda environments are conda environments that are created by you, the customer, and are managed by you. These conda environments are stored to the object storage bucket, which allows you to share them with your team, share them across notebook sessions, have reproducible models. It allows you to install them into jobs and model deployment. And then we have installed conda environments. So installed conda environments are the conda environments which are installed in your particular notebook session. Each notebook session will require at least one conda environment to run the notebook. These installed conda environments can be either data science conda environments or published conda environments. These environments are stored on your block volume, meaning that when you deactivate a notebook session and then you reactivate the notebook session, the conda environments will come back and you'll be able to access them in future notebook sessions. So let's wrap up what we talked about. In this session, we talked about conda environments being containers that stores collections of software. We reviewed the benefits of using conda environments. We introduced you to the Conda Environment Explorer. We also talked about the data science services having managed conda environments. We learned what a published conda environment was and that it's managed by you. We talked about environments needing to be installed in a notebook session in order for you to run your notebooks. And we talked about how you would be able to find which conda environments are installed in your notebook session. Thank you very much. Hello, my name is John Peach and I'm a data scientist on the Oracle Cloud Infrastructure Data Science Service team. In this module, you'll learn what a data science service conda pack is. In this lesson, we will introduce you to various conda environments you can use for your data science projects. Because conda environments can be challenging to create from scratch, Oracle has developed a set of pre-made conda environments built upon open source software that you can download and customize to suit your specific needs. The Data Science Service offers a series of data science environments that you can access through the Jupyter Lab Launcher tab by clicking the Environment Explorer. All data science service Conda environments come with the OCI Python SDK as well as the ADS SDK. Most Conda environments will have the publicly available version of Oracle ADS. The public version does not have the Oracle Labs AutoML and model explainability options. These two features are found in select data science Conda environments, such as the general machine learning for CPU or GPU Conda environments. Types of Conda environments. Some Conda environments are based upon an application. For example, a Conda environment for Onyx or PyPGX or PySpark. Other Conda environments are based on the use case, such as computer vision, data exploration and manipulation, financial services. Each one of these Conda packs have a select best-of-breed software built in them to match the tasks or the application that you're trying to work with. Conda environment families. Condas are grouped based on the Python version in the environment and the architecture. For example, the natural language processing Conda pack has the following versions. You have natural language processing for CPU, which is the architecture, Python version 3.7, version 2, and if you notice, the third item on the list is the same thing, but it's version 1. So the difference between these two versions is a change in the software that's provided, but they both run on the same architecture and both have the same version of Python. Another example, the general machine learning Conda environment. Each version is that's being shown here only has a single version, and we've gone from general machine learning for CPU Python version 3.6 version 1 to general machine learning for CPU on Python 3.7. There is generally a naming convention used for the Conda environments based upon its use case. So application-based Conda environments have their name based on the software, the version, and the architecture and the Python version. For example, PyTorch 1.10 for GPU on Python 3.7, or TensorFlow 2.7 for CPU on Python 3.7 version 1. For use case-based Conda packs, the naming convention is the task for an architecture on a Python version. For example, data exploration and manipulation, that's the task. For CPU, the architecture on Python version 3.7. Some older Conda environments do not follow this convention. Let us talk about some popular data science Conda environments. The first one is computer vision. Computer vision is a subfield of artificial intelligence. Computer vision derives information from images and videos. The computer vision for CPU and GPU Conda environments includes some of the most powerful data science tools for pre-processing images and performing computer vision tasks. Use the Conda environment for object detection, object tracking, stitching, compressing images, facial recognition, eye tracking, and much more. Some of the popular libraries that are included are scikit-image, Pillow, PyTorch, and the popular open source computer vision library OpenCV. This library includes several hundred computer vision algorithms. The data exploration and manipulation Conda environment contains libraries for ingesting and visualizing data sets. You can stream data from Oracle Cloud Infrastructure and much more. It's designed for doing exploratory analysis. It includes open source products such as ADS, which is installed for ingesting data from multiple data sources in OCI. You can also consume streams using the Kafka Python library. You will work with data frames using Pandas, Panda Parallel, Dask, create plots using Matplotlib, Seaborn, Plotly, and Bouquet to construct visualizations of your data sets. The general machine learning Conda environment is one of the most popular ones. This environment provides a baseline for generic machine learning tasks and comes with multiple notebook examples to help you get started. You can do things such as data manipulation, supervised machine learning, generic machine learning tasks. By that we mean there is a wide assortment of machine learning algorithms built into the Conda environment. This Conda environment also has functionality for auto machine learning using Oracle's AutoML and Oracle Labs machine learning explainability packages in ADS help you understand what your model is doing. The general machine learning library includes such things as XGBoost, LightGBM, Keras with TensorFlow, and as I mentioned, Oracle AutoML. This environment includes the model explaining library, Oracle MLX, which is distributed through ADS. Natural language processing Conda environment is designed for users interested in working with text data sets and performing natural language processing tasks. Such tasks would be text extraction, key phrase extraction, parts of speech tagging. The environment contains curated lists of libraries and frameworks common for natural language processing workloads. These libraries include NLTK, Hugging Face, transforming libraries, various wrappers around BERT such as KeyBERT, and natural language processing and deep learning accelerating frameworks such as PyTorch Lightning and Simple Transformers. ONNX is an open source format that represents machine learning models. ONNX is open source, open model, and allows you to save models from different types of model classes into a single portable format that is independent of the training library. It defines a set of operators that are used as building blocks. It provides a common file format to enable AI developers to use models with a variety of frameworks, tools, runtimes, and compilers. This environment is designed to test and execute your ONNX model artifacts. ONNX models can be deployed using the data science model deployment service. So it includes portability and operability between different frameworks. So you can develop a model essay in scikit-learn, save it in ONNX, and then when the ONNX runtime runs, it's not concerned with having scikit-learn or TensorFlow, whatever it was built on, does not need to be there. It will just execute as an ONNX file, an ONNX model. The ONNX runtime library allows you to run models on different platforms. Use this Conda environment to convert models from most machine learning libraries to ONNX formats. Then use the ONNX runtime to perform inferencing. Review the processing steps that your model makes by having the ONNX generate a graph of the model workflows. This environment is commonly used in model deployment as the base Conda environment, and not necessarily the Conda environment that it was trained on. Oracle Database. This Conda environment supports on-premise and autonomous database, ATP and ADW databases. Use this notebook to create ETL jobs, batch transform data, and perform database queries. It comes with such tools as IPython SQL, Oracle ADS, and SQL Alchemy. You can seamlessly work with Oracle databases using the ADS connector, SQL Alchemy, and IPython SQL. The ADS connector provides a uniform interface to connect to databases. Use IPython SQL to directly enter SQL commands into a cell without the need for Python in that cell. This includes support for Oracle databases, MySQL, SQLite, and general support for most databases. PyTorch is an open-source machine learning framework. It provides a wide range of algorithms for deep learning. Some of the high-level features include tensor computing with strong acceleration on GPUs and deep neural networks built on automatic differentiation systems. Common use cases include computer vision, natural language processing, and general machine learning. This environment includes acceleration support for Intel CPUs with the use of del4py, a library that enhances sklearn algorithms and using one of Intel's OneAPI data analytics library. This allows you to compute neural networks on a cheaper CPU than the more expensive GPUs. PySpark is a Python-based API for Apache Spark. Apache Spark is a framework for processing huge amounts of data on a distributed compute system. It contains the very powerful MLlib, which is a specialized library for machine learning. The Conda environment allows you to write your test code in a notebook session and then execute it on Dataflow, where Dataflow is OCI's Spark system. It includes packages such as Spark SQL Magic, which allows you to execute Spark SQL commands directly in a notebook. TensorFlow Conda environment is an ecosystem of tools and libraries to create state-of-the-art machine learning models. You can use TensorFlow to train and deploy deep neural networks for image recognition, natural language processing, recurrent neural networks, and many other machine learning applications. You can use the Oracle ADS library to speed up your data science workflows. Some of the important libraries that it includes, obviously, is TensorFlow, but it also includes TensorBoard, which provides a visualization tool needed for understanding your machine learning experiments. Let's wrap up. In this module, we have talked about what a data science Conda environment is, meaning that that's a Conda environment that is managed and curated by Oracle. We've talked about the types of Conda environments that Oracle manages. We've talked about what a Conda environment family is, its naming convention, and we have reviewed several popular data science Conda environments so that you can better understand their use cases and what key libraries are used. Thank you very much. Hello, my name is John Peach and I'm a data scientist on the Oracle Cloud Infrastructure Data Science Service team. In this module, you will learn how to manage Conda environments using the ODSC command line tool. Let's recap what Conda environments are. They're a collection of software that are bundled together. In the data science service, there are Conda packs that are managed managed by the data science service team. And there's also conda packs that you can publish yourself. A lot of the work can be done by using the Environment Explorer, which is a GUI to manage these conda environments. However, more control is given to you using the command line ODSC command. There's a lot of functionality within the data science conda management environment, and you can do things such as browse, which allows you to access detailed information about conda environments in a YAML format. It also provides information on the data science published and installed conda environments. You can perform searches. Use the command line tools such as grep to browse capabilities to search the conda environments. You can install conda environments, either the data science conda environments or the published conda environments. You can clone environments. So you can copy an installed conda environment to another location. This is a handy feature when you want to make major changes to the conda environment, but you do not want to break a working environment. You can modify a conda environment. You can change the contents of an installed conda environment, for example, when you want to upgrade a software package. You can publish a conda environment, where you store your customized conda environments in object storage. This allows you to share it with others and use it in model deployment and jobs. Obviously, you need to be able to delete your conda environments, and that's done through the command line as well. You can also create custom conda environments using a conda YAML file, and we'll talk about how to do that. Let's talk about browsing conda environments. So you can do this through the Environment Explorer, or you can do it through the command line. The command line uses a list command for browsing, and it gives you all kinds of information about the conda environment, such as the name, its description, what are the key libraries, and what the slug is, where the slug is the unique environment name. By default, you would use the command ODSC conda list, and this would give you detailed information about the data science conda environments. If you're looking for information on what conda environments you have installed, you would use that same command, ODSC conda list, but in this case you provide the optional parameter local. This will limit it to just the conda environments that are installed on your notebook. To access published conda environments, you would use the ODSC conda list override to override the default setting of providing data science conda environments to provide published conda environments. For this command to work, you'd have to have set up the object storage bucket and done an ODSC conda init to configure where the published conda environments are. Searching. There's no specific command for searching in the command line, but you can do searches through the Environment Explorer. To do it on the command line, you would do the ODSC conda list command, and then you can pair that with different command line tools such as grep to search for different parts of the YAML file. So in the example that we have down here, ODSC conda list pipe grep e, and then some regular expression to capture the name tag, and then another regular expression to capture the slug tag, will result in a listing of all the names and slugs for all the data science conda environments. You can combine this with all kinds of other powerful tools, such as awk and Perl, to access the information that you want. Installing conda environments. This is done through the command line using the ODSC conda install command. You provide the slug option and the name of the slug. You can get the name of the slug through the Environment Explorer, or as we just saw in searching, you can search for it. If you would like to install a conda environment that you have published to your object storage bucket, use the ODSC conda install slug, the name of the slug, and then the override parameter. And that will override the default behavior of installing data science conda environments and install a published conda environment instead. Cloning Conda environments. Users can copy an installed Conda environment. This action creates a custom slug for the Conda environment that you've cloned. So this is done by calling ODSC Conda clone, and then you need to specify the source slug using the from environment command line option. The source slug is the slug of the installed Conda that you want to clone, and then you can give your new Conda environment a new name using the EMV option. This will automatically create a new slug for you, and you'll be able to identify the Conda environment by the Conda name that you've given it. Modifying a Conda environment. It is common practice that you've installed a Conda environment and you want to install a new piece of software or change the version of something. This is not done through the ODSC command line tool. Instead, it's done through the Conda tool. So the first thing you need to do is call Conda activate and pass the path to the Conda environment that you want to work with. So by default, it's stored in home data science Conda, and then the slug is the folder name. This will, in the terminal, basically activate the Conda environment. So any changes you do will change that Conda environment only. So for example, if I wanted to upgrade ADS to the latest version, I would do Conda activate and then the path to the Conda environment that I want to change. And then I would do Python 3-m pip install Oracle ADS upgrade. And this would upgrade my version of ADS. Once I've cloned and modified a Conda environment, I might want to publish it. Publishing it takes the Conda environment and moves it into an object storage bucket that you can share with others. It allows you to run these Conda environments in jobs. It allows you to have model deployments using them, share it with your coworkers, and allows you to have reproducible research. So the first thing you need to do is you need to initialize the Conda bucket that you're going to use. So you would go into the console, go into your object storage buckets, and you would create a bucket where you want to publish your Condas to. From there, you would capture the namespace that's being used and the bucket name that you've created. Then you go to your terminal, and you only have to do this once in a notebook session. You call ODSC Conda init, which is going to initialize where the published Condas go. You use bucket namespace, and you give it the namespace for your bucket, and then bucket name, and you give it the actual name of your bucket. Once that's done, the system knows how to communicate with your object storage bucket. To publish your Conda, you very simply call ODSC Conda publish, and then -- slug, and then the name of the slug that you would like to publish. This will bundle up the Conda environment and push it to your object storage. If you no longer need a Conda environment and want to free up some space, you can delete it. To delete it, you call ODSC Conda delete, and then you give it the name of the slug, and this will delete the Conda environment for you. One way that you can create a Conda environment is by cloning it. Another way is by modifying it, or you can create a Conda environment from scratch. And you do this by using the ODSC Conda create, and then you give it the file name command line option plus the Conda manifest YAML file. So this is just your standard Conda manifest that you would use to create a Conda in any other system. By default, the ODSC Conda create will install some base packages that are stored in opt-base environment.yaml. You can use the -- empty option to prevent that from installing it. What is in there are the essential packages that are needed to work with the notebook session. So let's wrap up. We've talked about various Conda environment functionalities such as browse, install, clone, publish, delete, and more. We've discussed using ODSC command to perform many of these operations, and we've showed you how to combine the ODSC command with other Unix commands to do searching for the environment that you're looking for. Thank you very much. Hello, my name is John Peach and I'm a data scientist in the Oracle Cloud Infrastructure Data Science Service. In this demo, you will learn to manage Conda environments using the ODSC command line tool. You will learn to browse, search, install, clone, modify, publish, delete Conda environments, and we'll also look at creating a custom environment from scratch using a YAML file. The primary command we'll be using is ODSC. So if we call ODSC and look at the help, you'll see that there's a number of subcommands associated with it, and we're going to be using the one Conda. So let's take a look at what's available for that. So ODSC Conda. And what we see is there's subcommands like list, initialize, show configuration, publish, install, etc. We'll be going through most of these. So let's start off by browsing. So if we call ODSC Conda list, it will return back to us a YAML file of all the available data science service managed Conda environments. And it has tons of information in it. For example, we can get the name of the Conda pack, we can get the slug, which is a unique identifier for it, and here it's telling us that the type is data science, meaning it's managed by the data science service. We can use the same command, but this time use the local option, and it'll return back to us a YAML file of all the installed Conda packs on the notebook session. And again, we see the same information. We have the name, we have the slug, but here the type is local, meaning that this Conda pack is installed locally. If I wanted to see what was published, I would use the override command, and it would tell me everything that is available and published. I'm not going to do this now because we haven't set it up and it will fail. Let's take a look at searching for different information, because what we got back was a YAML file with tons of information that's hard to access visually when we're at the command line. So what we're going to do is use grep and other command line tools to parse that information. So if we do ODSC Conda list, so we're just going to list all the information from the data science service managed Conda packs. And we do grep -e, which is going to allow us to use a regular expression. If you don't know what regular expressions are, it's a search syntax that allows us to do pattern matching. So the caret that I have there means start searching at the beginning. These brackets say look for spaces, and the asterisk means as many spaces as we want. And I'm going to search for name. And that's going to give me all the YAML keywords for name. And I also want to look at the slugs. So let's do the same thing, but this time we're going to give it slug as the pattern we want it to match on. When we do this, it's going to go grab that YAML file again, and it's going to filter out anything that is a name or a slug as the keyword. Now we want to install a Conda pack. And I do know that there is a Conda pack that has data exploration name to it. So I'm just going to use the same string we had before, but I've added grep data exploration. And that's going to go out and it's going to get a list of all the Conda packs in the data science service. It's going to look at the slugs and just give me the ones that belong to data exploration. So to install that, it's ODSC Conda install, and then I give it a slug parameter and I tell it to install that. what it's going to do, it's going to go out and it's going to grab that package. It's going to ask me what version number do I want to use, because I can use a different version number than the number that is used by the conda itself. And it's going to download this, and then it's going to extract it. It's going to take quite a while, so I'm going to pause the video while it does that. We're back. It's installed the conda pack, and now let's just make sure that it's actually there. So we're going to use the ODSC conda list command, and this time we're going to use local because we're looking for the installed conda packs, and we're going to do grep. We're going to look for the slug parameter. And then we're going to make sure that the exact conda pack slug is there. So that's Data Explorer P37 CPU V3. So if this returns a result, then the conda pack was properly installed. And it did. The Data Exploration conda pack is installed. Now what we want to do is we want to clone it because we want to make some changes to it. So we're going to clone it using the ODSC conda clone command. And now we need to tell it from what environment, from what conda pack do we want to clone from. So we give it the slug name of Data Exploration Python 3.7 CPU version 3. And then I need to give it a name. And the system will automatically give it a slug based on the name. So I'm going to call it My Data Exploration. The system is now going to ask me what version number I want to use in my copy of the clone. I'm just going to leave it as version 3. And it's going to go out and it's going to collect up all the packages that it needs. It's going to build a big zip file, a tar file of everything, and then it's going to install it. So while that's happening, I'm going to pause the video and we'll be back when it's done. Welcome back. It's finished cloning the conda pack, and we need to determine what its slug was. So to do that, we're going to use ODSC conda. We're going to list, and because we're looking at installed ones, we're going to use the local option. I'm then going to use grep, and I want to get the names and the slugs. So it goes through and looks at all the installed conda packs. It came back and it told me that my Data Exploration conda pack has this slug here. So we're going to need this. What we want to do next is we want to modify the conda pack. To modify the conda pack, we're going to use the conda tool. So not ODSC conda, just conda. We're going to activate the conda. The conda is stored in conda. What we want to do now is modify the conda, and to do that we need to activate it. So we're going to use the conda command, activate. Now notice it's not ODSC conda, it's conda, and we're going to give it the path to where the conda is installed. So all the condas are installed in the conda directory, and we give it the slug name. So we activate the conda. Now any changes I make now will affect that conda. So let's do something like install the pendulum package. So it's going to Python 3. We're going to do a pip install pendulum. So that's going to go to pip. It's going to grab pendulum and it's going to install it. And now let's deactivate our conda because we're finished making the changes. And let's go on to publishing the Conda. So what we need to do here is we need to set up our Conda environment. Let's go ahead and publish our Conda. So the first thing we need to do is set up a bucket in order to store the Condas in. So if I go over to my buckets, I have my compartment I'm in, and I want to create a bucket. So the bucket that I want to create is called Publish Conda Environments. I'm just going to copy and paste that in here. And then it's just going to go ahead and just create the bucket with the default parameters that's there. What you need to note is this is going to be your bucket name, but you also need to know the namespace in order to configure this. So let's copy the namespace. Now we need to initialize the system so that it knows where to store and access published condas. You only need to do this once in a notebook. It's the ODSC conda init command. I'm going to tell it the bucket namespace and I need the bucket name. I'll just copy and paste that in. There we go. Once we're initialized, we can go ahead and do things like publish our conda. So to publish the conda, it's just ODSC conda publish. And then you give it the slug parameter, which is the name of the slug. So in my case, it was my data exploration version 1. This is going to go and collect up all the conda information and upload it to the bucket. While it's doing that, I'll pause the video. Welcome back. It's gone and finished uploading the conda to the bucket. So now that it's published, we can check to see if it's published by looking at ODSC conda list. This time we're going to use the override command. We're overriding the default location, which is the data science service conda packs. And what we're going to do is we're going to grab the names and the slugs of any published conda pack that we have. And so we see that we have the conda pack that we just published is listed there. Let's take a look at the bucket. So if we go to the bucket and open it up, what we'll see is that there's a folder called Conda Environments. If you go inside of that, it's listed by architecture. So we have CPU, My Data Exploration is the conda, and then version 1, and then here is the conda environment itself. Let's go ahead and delete that conda off of my notebook session. To do that, use ODSC conda delete. And then we need to give the slug name that we want to delete. So it is My Data Exploration version 1. This is now going to ask me whether or not I want to delete it. I'm going to confirm that I do, and we'll go ahead and delete it. We've gone over ways to clone and publish and install. There's one other thing you can do to create a conda, and that is to use a conda YAML file. So I have one here that I'm created. We won't go over the details of doing this, but we have a YAML file that lists the channels and their dependencies and all that type of stuff that you would need to build a conda file. And to do this in our environment, there's some extra things that get added in by default. So if we look at the up base environment YAML, these packages will be installed for us automatically. So to install the the conda using the YAML file. It's ODSC conda, and then we're going to create the conda pack. We have to tell it what file we want. So we're going to use our YAML file. And this will go ahead and create it. If I don't want to install the base dependencies, then I would add in the empty operation. So I'm not going to actually run this. I just wanted to show you that you can use advanced features like creating conda environments from a conda YAML file within the service. Thank you very much. Hello, my name is John Peach and I'm a data scientist on the Oracle Cloud Infrastructure Data Science Service. In this module, you will learn about why it is important to use the OCI Vault service to store your secrets. You will also be introduced to key concepts such as the different types of keys, key rotation, and storing your secrets in the vault and not in your code. Let us start by discussing what is the OCI Vault and why it is important to you as a data scientist. The data science workflow often requires you to interact with other services, to connect to important data, to store and retrieve artifacts, import and export data,